Hello, good afternoon, and thank you for joining us. My name is Amanda Sterkenberg, and I'm the content manager for Regenesis in Europe. And today I'm joined by Todd Harrington, Global Petrofix Product Manager at Regenesis, and Marcello Carboni, Regional Manager for Regenesis in Europe. Before we get started, a couple of admin things. If you experience any sound or connectivity issues during the webinar, then log out of the webinar, close your browser completely, and then log back in again to the webinar, and this should resolve any issues. Now, it may be useful to know as well that we're recording this webinar, and a link to the recording will be emailed out within the next couple of days to anyone who is registered. If you have any questions during or after the main presentation, that's great. We'll welcome them, and you can post them in the webinar interface panel. I'll collect all the questions and we'll do our best to address them at the end of the webinar in a separate Q&A session. We'll try to keep this webinar to round about an hour in length, but if we run out of time and we don't get to answer your particular question, don't worry, we will follow up with each of you individually via email. Also, after the webinar today, you'll receive an email with an attendance certificate already attached. So if you need one, you don't have to ask for this separately. And inside this email, there's also a link to a short feedback survey. Okay, that's all from me. I'll now hand you over to Todd for the main presentation.
Thank you, Amanda. I appreciate that, and delighted to be here today and presenting with Marcello on colloidal activated carbon, and specifically for a product that we have had out for a couple of years now called Petrofix. So we're going to be talking more today a bit about some of the research around its distribution capabilities that are third party. We felt that in providing a little bit of an update of this technology, it would be helpful to see some of the work that other people have done as they've attempted to get delivery and injection on some challenging sites. So in terms of organization, it's going to be pretty straightforward. I'm going to get into some of the basics of colloidal activated carbon and some third-party work on testing its distribution in the field. I and Marcello will get into roughly 4 case studies for you, which we think highlight some of the best attributes and some of the best practices of these technologies. We will actually get into, I think, some needed best practices, things to always consider when doing a design or being in the field that I think are really important for the success of your project that are often missed. And then we'll have plenty of time for a Q&A towards the end. So jumping right into it, colloidal products might be new to people in this webinar, and there's been a number of ways that we present them in the past, but the development of colloidal technologies here at Regenesis began with our desire to see if we could improve our ability to inject a single technology and overcome the challenges with rebound, specifically through the phenomenon of back diffusion. The idea with back diffusion is that you can clean out contaminants in main flux corridors of an aquifer, but contaminants that have moved into, as we call it, storage units, which might be clay or silts over time, can come back out into the aquifer and recontaminate it after you've spent a lot of money doing that. So it could be anything from excavation, it could be anything from in situ chemical oxidation, whatever technology it is. Can you get to the cleanup goal that you're looking to, well, to get to the cleanup concentration? And what is that differential? And can you get below it? For many remedial practitioners, this has been a challenge over the years where they might be on the 3rd, 4th, or 5th technology. And many times it was not having a technology to get past this back diffusion gap. So that's where Regenesis started this research back in 2007. And we were just trying to get over the feeling of, like the Greek god Sisyphus rolling a ball up a hill, a boulder, and having it come back down, in this sense of the remediation technologies we're using and not getting to closure. So here's a graphic that we've used a few times, and you're going to notice that I use a lot of black coloration in an aquifer where contaminants move, because we're going to be talking a lot about activated carbon today. But the idea for a good product to treat back diffusion or to treat the movement of hydrocarbons in general, is to get something that can fully move through the same flux zones and corridors that contaminants themselves move through, so that the product itself is not a hindrance in of itself in moving the aquifer. Certainly, you're going to want a multi-year lifespan. It takes time for contaminants to move out of, say, storage units or clay into high flux zones of an aquifer, and ideally would treat a broad range of contaminants. So our research focused very heavily on, ultimately on the use of activated carbons, but we did look at various other chemistries, including polymer chemistries. It was extensive. We did 6 years of research looking into this and ultimately developed a colloidal technology based on activated carbon. That research concluded in 2012, where we started beta testing these products in the field, the first being Plume Stop, and also ultimately has resulted in 7 patents covering the use of colloidal technologies to treat back diffusion and other properties related to them. So we won't be talking about Plume Stop today, although many of you may have heard about it, and it was released in 2014. But there were some limitations in terms of how easily it was to use Plume Stop to treat hydrocarbon plumes. And so a new formulation of colloidal activated carbon originally developed was reformulated and launched as the Petrofix product line really towards the very end of 2018 and into 2019. So in terms of creating that, let's move into more of a set of slides talking about the differentiation of colloidal carbon. And the reason I wanted to do that is that activated carbon has been on the market for quite some time. Obviously, people are quite familiar with it in terms of water and wastewater treatment, in terms of pump and treat systems. For many of you, you're very familiar with it in the use of in situ remediation. However, colloidal carbon does sometimes get confused with activated carbon in general, and there are some very important differences that matter when cleaning up sites. So with the concept of trying to get a material into a flux zone that completely follows the same channels that contaminants will go through, the challenge with granular carbon or powdered activated carbon, first and foremost, is they're just too large to go into a lot of the soils that we're going after. If you look at the typical particle size of 400 to 1,000 microns for granular activated carbon, or say 300 to 250 microns in diameter for powdered activated carbon, they're physically too large to go into soils. For example, if we just look at some basic pore throat openings for some common soil types, for medium sands, the typical opening between particles is about 80 to 50 micrometers, and for silt, it's 3 to 8 micrometers, as shown in this table right here. Colloidal carbon has been milled down to the size of 1 to 2 micrometers, very, very small, size of a red blood cell. It's the only product that actually can move into or diffuse into silts of the two. So that's going to become very apparent on how important that is in the following slides. So a different set of pictures I really wanted to show for this webinar that we haven't shown that much before is that a number of years ago, and this was after the launch of Plume Stop, we did start to work with universities and other consultants who are doing research for testing and looking at the distribution capabilities of colloidal carbon just to get that verification. Now, we did work with Colorado State University and Dr. Tom Sale and one of his students, Kevin Saller, to do a flow-through experiment that was copied off of some earlier work that they had done for the Strategic Environmental Research Development Program grant that they had won for back diffusion. So I'm not going to get into all the details. This flow-through microcosm wasn't just put together to show the flow of colloidal carbon. It was also to measure the enhancement of biodegradation, its ability to handle back diffusion. But for purposes of what I'm trying to emphasize today, the ability to chase contaminants through the flux zones are going through. I want to show this to you. So this plexiglass microcosm has interlayered sand in brown and silts in white. And we flowed colloidal carbon from the bottom through the top for over 50 days. And you can see by day 2 that in the sandy zones, we are seeing nice movement and coating through that zone. By day 53, we've seen complete movement through the flux zones, as we like to call them here. And more interestingly, we're actually seeing diffusion into the silts, which are the white material. So at the end of the experiment, in this research setting, in this university setting, we did open up the microcosm. We did scrape back a bit of the soil to minimize any skin effects. And indeed, we did see the exciting effect of colloidal carbon evenly coating sand zones here. But more exciting, we noticed that particularly where we put the material in from the bottom, we started to see a nice permeation into the silt. So that helps verify that this actually can go into tighter silt soils. But more exciting, I think, is how does it function actually in the field? And is there any other third-party research on that, of the distribution advantages of a colloidal carbon over, say, using powdered activated carbon on the market? A gentleman named Rick McGregor, he owns a company called In Situ Remediation Services out of St. George, Canada, is an internationally recognized injection expert in a variety of different technologies, and particularly so also in activated carbons. He undertook, under his own funding, a study where he injected colloidal activated carbon alongside powder activated carbon at 4 sites and did an extensive number of soil samples to try to find where these technologies were going and if there were differences between the two. This was published, by the way, in the Journal of Water Resource and Protection, issue 12, in 2020, if you should like to look that up and obtain it. But the key is that he did side-by-side test plots where on the same site he injected colloidal activated carbon and just a few meters away injected powdered activated carbon on equal spacing over the exact same vertical injection intervals. And then what's unprecedented, and you don't see this that often, is that he took 520 soil samples after he injected the carbon technologies, both within the target injection zone, but also above and below those injection zones to try to see where the carbon went and if it stayed in where it was supposed to go. In this case, he did take total organic carbon, which is, you can use that analysis to actually look for activated carbon in the soils as a technique to look for that. It actually does work. So he did that approach, and then in his paper, he put together a lot of colorful isoplusts where he transected different vertical profiles and horizontal profiles for looking for that. So let's just look at the statistics and a couple of the pictures. So what he did find, which is very interesting, is if we're looking at the upper right, this very nice blue isopluth is actually atypical. All of the transects he did horizontally look the same for colloidal carbon. He was finding it pretty much everywhere he took a soil sample in the treatment zone. And he found it 94.4% of the time, whereas powdered activated carbon wasn't always detected, or if it was detected at very low concentrations. So he detected it at least at low concentrations 42.4% of the time. So this is looking good for at least colloidal carbon distributing horizontally. And let's look at it vertically. He also plotted the results vertically in transects on all 4 sites side by side. And this is just taking site 3. All the other sites look the same. And noticing that when measuring for total organic carbon through the gray target zone, which is where he put his injection rods to try to put it, the colloidal carbon did stay in the injection zone and appeared to really flood in evenly top to bottom through that treatment zone, which was pretty exciting to see. Whereas the powdered activated carbon, one of the challenges noted in the paper and that other people have noted in presentations and other papers is that powdered activated carbon, because it's so large, has to be fracture injected using high pressures. We're talking above 15 bar, 20 bar to get in the subsurface, and the carbon tends to shoot down those fractures, which could be usually about a centimeter wide. And as they're shooting down that, there has been some concern that they might go into monitoring wells and move up and down the monitoring well pack. So interestingly, that was something that he explored as well in this study. And what he did as part of the soil course he took is he drilled right down the monitoring well boring well pack right next to the PVC in the boring, and then measured for total organic carbon and plotted those. So here's two sites. And so what we're looking at is we're looking at percent by weight in the soil of total organic carbon of colloidal carbon here on the left, powdered activated carbon on the right. Colloidal carbon on the left, powdered activated carbon on the right, over the monitoring well screen for this particular location, two sites. So what he did find is that the powdered activated carbon indeed was accumulating in the well pack. It was accumulating to the point that there was 224% more powdered activated carbon in the well pack itself than in the adjacent formation. So it seems like there was some preferential enrichment in that case, whereas for colloidal carbon, he noticed that it appeared to not accumulate at all. In fact, the colloidal carbon itself was found at lower concentrations in the monitoring well pack than in the adjacent formation. So really kind of looking at what that might mean is that it appears from the results of the study that high pressure, sure, you can put this into clay soils. It's touted as a benefit of using high pressure to get powdered into clay soils, but it can be unpredictable. If it intersects wells, utility corridors, excavations, it's very uncontrollable, and it does have well impact. So it brings into question the ability to sample that well. Whereas a colloidal carbon, so we're talking about plume stop, Petrofix, pressures were much lower to use. In fact, they were about 10 times lower to get this material into the formation, according to the paper, and no noted well impact at that. So you could actually sample and have confidence that when taking samples from the well, that you're getting good results. So really, I hope that made a case for just the ability to distribute colloidal carbon uniformly, predictably, and reliably at a site for you. So I think those are the points I wanted to make there. And so I'm going to transition to a couple slides on the, what is Petrofix? So let's get into that a little bit, as you may be wondering, and then we're going to get into the case studies. So Petrofix is shipped as a concentrate of the suspended colloidal carbon. We spent a number of years figuring out how to mill this material. It's very challenging to do, and but we've been able to get it to ship to the field as a stable suspension that has over 30% by weight colloidal activated carbon, so quite a bit of carbon there. And that material, though, is diluted in the field to an injectate, which at that point that it's diluted, we do add currently ammonium sulfate and sodium nitrate to kickstart biodegradation. And when not getting into a lot on the biodegradation aspects of the material today, but it is a double technology. It's adsorption and biodegradation together. So we're not just absorbing contaminants, but we're using sulfate and nitrate as electron acceptors to stimulate hydrocarbon bacteria that are already in the formation. So very nice to have that together. And so with those together, the material is injected into the subsurface. And when it's injected, the best way to think about how it attaches to soil is it's similar to the way ink attaches to paper. And it attaches as a very thin coating on, say, a sand particle. This is a sand particle in an image we have shown for many, many years. But this sand particle, which is roughly 50 micrometers in diameter, has a roughness to it. This roughness is not the sand particle, it's the petrifix, it's the colloidal carbon that's adhering to it in a very thin layer. Notice the large pore space. Notice the large areas for water to pass through. This material does not clog an aquifer. It is only occupying a very small percentage of an aquifer volume, and we are allowing water to pass through, and benzene will absorb out. And once it absorbs out, bacteria are being stimulated at the same time. They usually don't have the nitrate, sulfate, or even oxygen that they need to biodegrade contaminants, but they start to proliferate. They'll form biofilms. Those biofilms will be on and around the particles, and you will be able to permanently destroy benzene and other contaminants. And when you do that, it extends the lifespan of the material itself. So we definitely have a multi-year longevity for this technology. All right. Technology has been out. We're approaching roughly 5 years now. It's been quite successful in Europe. We've done quite a few sites in Italy, and it's been quite successful in the world. We are looking at about 840 sites worldwide and nearly 200 in Europe alone. So we've seen some pretty wide acceptance and some good results that way. All right, let's just transition to, I would say, some of the more interesting things, like how does it really work on real-world projects. And I'm going to show a couple case studies here up front that I have shown before in other webinars. I was talking with Marcello, and we don't think as many people in Europe may have seen these, but this first case study I think is a really good case study because it represents a site that might be your site. It might be a site where you're on your third, fourth, or fifth technology and you're struggling getting groundwater to clean up targets. And this is also a site that they adhere to our best practices, and we're able to see some pretty phenomenal results because of that. So this petrol filling station, as I alluded to, was actually in Colorado, state of Colorado, and it operated as a petrol filling station in the Denver area until 1992. Now, it did not have the proper anti-corrosion system in it. The tanks did corrode and created quite a large release from the storage tank. It is a mix of clay, silt, and sand. This is typical for the geology in this part of Colorado. And the previous remediation strategies had gone on for a number of years. They had, it's actually a little bit longer than this, but from 04 to 2017, they had implemented 3 different technologies. So what's interesting is this image on the right, it says on-site building slab on grade. This is where the original tank was. And they wanted to develop this into a new commercial building, new storefronts. And so this site started out using soil vapor extraction, in which they successfully removed 703 roughly kilograms of hydrocarbon, at which point they wanted to develop this property. So they actually decided to dig out as much soil as they could during the excavation, and they dug out 650 cubic meters of soil. And then when they built the building and put the slab down, they put soil vapor extraction piping along the foundation and then across the road to treat the larger plume that had gone off site. And then they ran that for a number of years and successfully got out about another, say, roughly 2,500 kilograms of contamination. But still at that point, the plume was pretty contaminated, pretty broad, and the additional remedies were looked at. They did try a powdered activated carbon injection. It indeed had to be fractured in, as I talked about earlier. However, those fractures were unable to intersect or actually make contact with the contaminants. So then they transitioned and tried a chemical oxidation technology. But because of the clay, because of other the challenges of the site, this is the plume that they were left with, which was I think over 300 square meters, still at relatively high concentration. It so happens that Petrofix was released at about the time that they were looking at doing a second ISCO injection, and they decided to do a Petrofix injection under our guidance, and we actually used our crews to inject it out here. And so you can see on the figure on the right, where we injected, we were able to inject along the edge of the building. We were unable to inject in the road, but we were able to inject over the majority of the plume offsite here. The project was completed in September 2019. We injected 13,400 kilograms of Petrofix or colloidal carbon, 670 kilograms of our sulfate nitrate electron acceptor blend that I discussed earlier. We did 75,700 liters into 111 injection points at relatively low pressure, only 2.75 bar. We had very little surfacing at the site. You can see the spacing here. The spacing typically stayed between 1.5, actually it was closer to 2 meters, but no farther than 2 meters in most locations, which was our recommended spacing. Now I'm going to divert really quickly, and I'm going to come back to this after we're done with the case studies. But one of the challenges, and I would say an Achilles heel of remediation in the industry, is of not exactly knowing where the contaminants go. We spent a lot of time working on a great design with great chemistry, and the goal, though, of putting products in the ground often has more to do with the days in filled or gallons versus, I would say, a better goal of distribution, of actual true distribution. So we spent a lot of time actually using one of the great properties of Petrofix, that it's black, it acts like an ink, and we use that coloration as a tracer, and we can use that real time. So this very site used us as a tracer, and we looked for this in the flux zones, we looked for it in monitoring wells, and we didn't see it. We made slight adjustments to spacing, adjustments to volumes on the spot, so that any time we stopped and looked, the soil would look like this. So these are the actual sandy or gravelly flux zones between clay at the site, and these top cores are vadose zone above the groundwater where we were not injected. So that helped us attain overlap because we were able to see water samples pulled, we were seeing the telltale black coloration, and we were very confident that we were getting overlap there. So always plan to make adjustments in the field as part of your operating procedure. So the results were pretty wonderful. Pre-application, this is what we had. Post-application, by the first sampling event, or the first time we were able to get samples from all monitoring wells at the same time, which is roughly 9 months later, we showed tremendous reductions. We're talking non-detect to 99.9% reductions at 9 of the 10 wells. We had one well that resisted. It had an 85% reduction, but we believe because there was a concrete sidewalk here, we were not allowed to inject around here, and the consultant, we believe that prevented us from getting to some contamination. But these are some really wonderful results. Looking at the results vertically, it just shows the same, that BTEX was as high as 20 milligrams per liter, going to non-detect or below the tier 1 closure limits that they needed to get to out here, both for that and total petroleum hydrocarbons and gasoline. This site was closed and developed into a commercial property, so there's no further monitoring after 18 months because the wells were destroyed, but very successful after roughly 15 years of attempted remediation. Okay, one more short case study before we transition to Marcello, and actually two quick ones, but this case study is something unique that we've been talking about quite a bit in the US. It's the idea of flooding an active UST tank basin at a petro filling station. Why would we consider that? The idea of this concept was brought to us by our client. So imagine this. You have an active petrol filling station, and you're spending a lot of funds to clean up the contamination around the site. Well, the one area that people typically leave alone or have trouble accessing are the tank basins and utility corridors that are still being used, and those often accumulate high levels of groundwater contamination or even LNAPL that can be ongoing sources into the very soils that you just cleaned outside of that. And so this was an attempt to supplement site-wide remedial efforts in a shallow bedrock dense infrastructure geology so that they did not get recontamination over time. So simply what we did is we very carefully hand augured. There's different ways to do this, but we hand augured some very shallow points above the active tanks that didn't extend more than 0.75 meters below ground surface, so that we were not puncturing anything, we're not hitting anything. And you can see anything that says IW, like -07, 08, all these rectangles are where we decided to flood Petrofix over these 4 tanks, which were 3 37,850 liter tanks and 1 roughly 45,000 liter tank. The pressures were low. We actually pilot tested it because we had never done this before. We just did 1 drum of Petrofix, roughly 180 kilograms of Petrofix, just enough to get dark water. And we put it with 4,500 gallons of, should say 17,000 liters of water. I missed changing this, but 4,500 gallons of water. And using that, which was less than 20% of the pore space of the tank basin that was saturated, we didn't need to fill the whole thing because we trickled over the top. We were able to really get full distribution in that tank basin. And so this is a cartoon of what we're doing here, is that we're putting Petrofix in and around, drizzling it over these tanks. Now these tanks had, the leaks had been fixed, but this is showing an animation of, just to show what we're doing. And so we're filling this whole basin with this, and this is what we were doing here. We were able to do this with very low pressure, less than 0.2 bar injection pressure, no surfacing. You can see us doing the actual application right there. And then before we applied the Petrofix, you can see that benzene was at some reasonable concentrations, a few hundred micrograms per liter. But when we're looking at xylenes and some of the total volatile petroleum hydrocarbons, they're at much higher concentrations. So this is the before snapshot. And this is after putting Petrofix in for 2 consecutive years. We were able to get to non-detect or very low concentrations in the case of xylene. And so this was so successful that we were able to maintain BTEX below what was called Tier 1 risk-based screening levels for 6 consecutive quarters. And only 1 single well exceeded Tier 1 at quarter 6. Everything else stayed low, and the site was granted closure in September of 2022. So exciting stuff. And finally, before transitioning to Marcello, this is a quick show of the use of Petrofix for barriers. We do a lot of barriers in Europe. We do a lot of barriers in the United States. And the idea is to prevent contamination from going into a lake, crossing a property boundary. In this case, this was a bit of a stopgap for a site in the state of Montana that had many sites, more than 4 petrol filling stations that had been leaking over a number of years around this location, around this intersection, and causing high levels of contamination to go into this lake that was called Flathead Lake in the state of Montana. So the consultant did quite a bit of research to find out where the contamination was, and this high-res investigation that they did also found that they realized that the amount of contamination already going into the lake was much higher than they anticipated. And so they wanted to remedy this quickly. Now, they put in the barrier years before they have actually come out to do the source treatment remedies. And so they used Petrofix. In this case, they put in a 5-barrier Petrofix barrier. Many times we can just do a single barrier, but this was the first time this consultant had done this. and he put in a 5 barrier here based on the site characterization that he had done to prevent this from going into the lake. So just graphically, what we can see is he did take soil cores. He knew where the flux zones were, and he was making sure that where he had high flow and sandy materials that he was actually seeing the petrifix or making adjustments if he didn't. And the results are pretty wonderful. You see, this is before the barrier went in, and the concern is that this plume is continuing to move towards the lake at high concentration. But with the petrifix barrier for 3 consecutive years, so this is from 2020 to right now, it continues to go. They are continuing to get non-detect there. So this is the type of performance that you can see with a barrier. So with that, I would like to, I'm going to go ahead and transition over to Marcello, who can get into his case study.
Thank you, Todd. And here, with my case study, we are going to Europe, and more specifically, we are in Italy, in one huge town in northern Italy. This site has quite a long history. It was in the past century a thermoelectrical power plant, basically supplying electricity to the residents and to the surrounding manufacturing industry that were in the town. Then the site went dismissed. It went through decades of abandonment until when a new property owner came in and they decided to build their new office headquarters. The site comes with a contamination that it's located basically in this portion of the site. It is very heavy hydrocarbon, so long carbon chains. It's not diesel, it's not gasoline, probably it's about heating oil. So lower mobility and more difficult to biodegrade generally. This contamination comes into the soil, into the capillary fringe, and also into the groundwater. We are in a very permeable formation. It's basically gravel and sand. We are very close to a river, and groundwater, it's flowing very quickly. We are about 1 meter per day or even higher, so about 400 meters per year seepage velocity, which is a very challenging condition for our in situ technology. Basically, the quickest is the seepage velocity, the higher is the flux mass that you need to manage with Petrifix. So what was the strategy? For the soil, they decided to excavate. This excavation was not just for removing contaminated soil. Basically, they went for excavation on almost the entire site. They wanted to build underground parking, so 2 floors of underground parking. These removed the majority of unsaturated soil and also the contaminated part. Here in the cross section, you can see the structural system that they put in place for allowing the vertical excavation. On the capillary fringe, they decided to go for immobilization. So it was basically a jet grouting system. You can see here this gray rectangle in the map, and it's the same gray rectangle in the cross section. So immobilizing all the layer between the fluctuation part of the groundwater and capillary fringe. This was still leaving an existing plume exiting the boundaries of the site and going in below public street. So for the plume, the decision was to go for an injectable permeable reactive barrier using our Petrifix. And you can see here, it's like the installation of injection wells. for this injection and for the management of the residual plume going out. So first of all, this is an example of petrofilms injected into wells, not with direct push, which is most common examples, and also what you mostly have seen with what Todd has shown you with his case studies. So petrofilms is perfectly injected also into wells, so the size of the colloidal particles are perfectly able to get out of the screening of the well. It's not very common because it's a one-shot injection, so you're not looking for multiple campaigns, so injection into wells is less common. The screening was for 1.5 meters, so basically targeting the shallow portion of the aquifer, which is also the portion that it's contaminated. And here you can see the location of these injectable barriers. Basically, it's not linear, it's got a shape as an L. This is because of the direction of groundwater. So basically, we didn't want that on this right portion, there could be a risk for still the side part of the plume exiting the site. As you can read, the spacing was very high. We used 4-meter spacing. This is, I would say, over the high end of what we would recommend. Also, if you refer to what Todd has I've said before, we usually go for much tighter spacing. So why is that? Basically, because when they were realized very well, this was much before selecting petrofilms, and indeed was much before petrofilms was launched. So at the time they did the excavation, still they didn't have a remediation plan ready to be submitted. So they needed to advance with the building of the new structure. So they excavated, they left their injection points available for any future remediation technology to be selected. And then they continued on with the building of the parking space and then the rest of the building. And this is also the reason why they did select for injection wells. It's because once the building was there, this area was completely inaccessible for any direct push rig. So even the smallest one could not enter. So in order to allow the in situ remediation, they brought forward the installation of a well. So we went injecting, and then it was years later the installation of a well. So it's not a spacing we would typically recommend. In this case, I would say we have been quite lucky. I think I would say we have been also supported by the fact that in this specific case, it's a very highly permeable geology and also quite homogeneous, at least in this shallow portion. The injection went through 1 week of activities. It was pretty challenging because the building was already there. So we needed to have a lot of caution, in, especially on not to damage the pavement, the structure, etc. We did cover everything with plastic liners. On the left picture, you can see the mixing area. This was on the backyard at the ground floor. So then we did deliver the product through our high pressure hoses through this ventilation grid. So then these pipelines went down to the floor -2. And injection into wells, it's pretty similar as a concept to direct push, but what we do is that we insert an inflatable parker inside the well in order then to allow the product to get in and not to have any daylighting on surface. But even if we're using inflatable parkers, the pressure range we are using, it's I would say same range as direct push injection. So in this case, probably we didn't even go higher than 1.5 bars. And here are the results. So first of all, in this site, the consultant was measuring hydrocarbons with two different sampling measures. What you see on the left graph is called dynamic sample. This means low flow purging, stabilization of the parameters, and then low flow sampling. On the right side, instead, you're seeing samples taken via baler. So before starting low flow purging, they were taking a static sample through a baler. Baseline values were already since the beginning very different. So some few thousand of micrograms per liter with a low flow sampling, hundreds of thousands of micrograms per liter with a baler. This difference has been accounted by the consultant by the fact that this is heavy hydrocarbons. But you need to think that basically there was a sheen, so an iridescence on top of the groundwater, so not really measurable an apple layer, but some unmeasurable layer being on top. So this is also the high end of the applicability of Petrofix. So it's not a technology that would target measurable levels of an apple. So what happened with injection? The decrease in concentration was continuous and very, very evident. Mind that the graph on the right is the y-axis is in the logarithmic scale. This is just to allow and make more visible the decrease in concentration. It is not really fast, so it went through a large number of months before getting to the lowest values. I would say it took longer than what we would expect from a Petrofix application on average. Usually we are expecting some few months for the decrease in concentration. But anyhow, it shows the typical stable trend that Petrofix usually provides. So compared to other technologies, we are not expecting a fluctuation of the concentration, we are not expecting rebounds, etc. So those results are in the injection well themselves, so they are wells, so they can be used both for injecting and then for monitoring. These graphs instead are for the compliance monitoring wells, the point of compliance, which are meters down gradient of our barrier. So those are already on the public street. So also there we could see a decrease in concentration. It's much more evident from the samples taken by the baler because it was showing a much higher initial concentration. So it went down again quite quickly and providing stable concentration. The target here is for TPH 350 micrograms per liter. This has been reached in a stable way and on the long term. Here I'm showing you the monitoring until the end of last year. The site is still under frequent monitoring and it will continue like that for the for time in future. And this is to ensure that the barrier is continuing to work. So after this case study, I'll hand over again to Todd, and we will see each other later for the Q&A session. Thank you.
No panic, Todd. I can see you have some issues. Is your sound working?
Yeah, okay. We can edit that out, right?
Yeah, no problem.
Okay, all right, so let me,
I think once you're ready, we'll do the handover again, Marcello.
okay,
So I have a good
right.
editing point.
All right, am I showing my video right
Yes.
now?
Your
Okay,
no, not your video, but I see your screen, and that's the right
okay,
screen, so that's good.
okay. Do you want to try the handover again with Marcello?
Yeah, I'm gonna make him
Okay.
presenter again. Just have your last slide up again, Marcello.
Yep.
I'll mute myself again.
Okay, and with that, I will hand over again to Todd, which will present you key tips on injection, and we will see each other again later for the Q&A section. Thank you, and up to you, Todd.
All right, thank you, Marcello. That was great. All right, so I know that we're approaching our time here, and we had wanted to provide some tips on best practices. This is something that we don't talk about a lot, but let me just say for those members in the audience that are approaching or considering Petrifix sites over time, that I and my team, as well as Marcello and his team, are there to talk you through even doing pre-application calls, discussions back and forth. We desire to help you cradle to grave in the field. So I just want to let you know that. One of the concepts both Marcello and I have been talking about barriers today, and some of the best practices revolve around the fact that Petrifix doesn't continue to migrate. So it looks like an ink and you might think it's just going to keep migrating forever, and it doesn't. This is a column study that we did where we were measuring treatment of diesel, but what I want to point out is that on the right was the column that we put Petrifix in, or colloidal carbon in, and kept dosing it 15 times and kept flooding water through this column over about a month. And we had no Petrifix come out of the bottom of this column through the entire time. What happens is the material sticks to soil and stays in place. And so for barriers, that's why it can be very effective. Now, on very fast flowing aquifers, yes, you might be able to push this farther than we want it to go, but we have techniques to deal with that. So very controllable. So given the fact that this doesn't keep migrating, you cannot rely on the same techniques that you might apply for, say, solvent treatment, where you're using electron donors, and you can use electron donor sweep through the advective movement of groundwater. So what you need to do is you need to really stay on good orientations of injections with wells or grids, and have a really good remedial conceptual model so you can lay things out correctly. So let's just look at the pictures. These are actual mistakes that I've seen in field. But the good is if you can completely get overlapping coverage with your injection points to your wells. The typical spacing is going to be somewhere around 1.5 to 3 meters. Typically 3 meters would be a stretch, so let's say 2.5 meters on most sites without pilot testing. So be careful where you place grids. Sometimes you'll leave a monitoring well out and not get coverage. You can do a terrific job treating a source area, but unfortunately you're not going to be able to monitor that progress. Unfortunately, I've seen that typically through piping or logistics being in the way. Just be cognizant of that. Another thing is not only with gaps in coverage that might be around key wells, keep in mind that as water passes through a barrier, the distance to the monitoring well that you might be using to monitor the performance of that barrier is very important to know. For instance, if you do a barrier on one side of a road, and then say 10 meters or 15 meters on the other side of the road is the well, if groundwater's slow, it could take a year before you see any results, and you need to be aware of that or change where you put the barrier. And the other thing is this orientation. I had a client work on a bedrock site once, and they didn't exactly have the groundwater flow directions right. They thought it was moving more of an arc, but actually they had what we called a glancing blow, where things went right by it. So really just good proxemics, good spacing will overcome a lot of challenges. And taking that into consideration, you know, if you have good spacing, good layouts, and all that, you need to make sure that you're putting in the right volumes, and staying on and not stretching. We call it administrative pressures. There is a situation where you might feel like you don't have the budget to necessarily do the number of points that you need. I would suggest that it might be better for you to carve out a smaller part of your site and focus on that versus necessarily stretching the points out to where you have large gaps. The way I like to say it is when I'm asked the question, what is one of the biggest challenges with Petrifix? Really, one of the biggest challenges is not its chemistry. One of the biggest challenges is poor distribution in the field, where people are not paying attention to this, and you take activated carbon with electron acceptors, all well documented to work, and they're stretched out too far, and benzene just slips right through. So watch out for that. So spacing is important. Filling up the right amount of aquifer pore space, one of the biggest design variables that Regenesis spends a lot of time thinking about is when we go into the field, we talk a lot about effective pore space filled. And that is how much of the mobile porosity the contaminants are moving through do we want to displace and put Petrifix into? Well, I can tell you that our designs have that in them, and we're looking usually at least 50% of the pore space filled for most sites. Sometimes that's lower, definitely lower for bedrock or maybe a tighter clay with thin sand seams. But certainly for sands or for barriers, you want to stay above 50, if not above 60 for barriers. So be attuned to the water usage, the spacing, and if you do all that, and then one thing I want to challenge you with is consider that your site is dynamic and that we've done the best thing that we've done the best that we can without pilot testing to look at your site to make good engineering judgments about dose rates, about the type of equipment to use in the field, et cetera. And even with all of that, we might be in close to where we need to be, but we might need to make some adjustments. And that's where my prior discussion of looking for the product, using it as a tracer, looking for it in wells, looking for it in temporary piezometers, looking for it in soil. If you can give yourself a half a day, give yourself a couple hours, put it in the bid to allow yourself the flexibility, that alone, that half a day, that 1 day of flexibility might prevent you from having to come back out again for a second injection. So very important, something that we spend a lot of time about. So really, I'll just go through these really quickly. We do have recommended tips. If possible, the tip that we like to use when available is a pullback screen. They come in different sizes. The idea is that you push them down to the aquifer and pull back towards the surface to expose these. These were typically used for water sampling, but they work pretty fantastic for putting Petrifix in the ground. And why is that? It's because when you expose a long screen with many holes, you can keep pressures low and allow the Petrifix to find the paths of least resistance. This is the tooltip that I would recommend that you try first. But there's certain sites that might be tight, that might be hard to put it into, and you might have to have secondary tooltips, in which case the more familiar expandable tips or pressure activated tips are acceptable. The only thing that you want to consider is that when you push those down or pull them up, you probably want to just inject every quarter to every third of a meter and not pull large intervals to leave gaps. So that would be the only change that you need to do with those. But as I said, we're happy to talk through those with you for any projects that you have. And finally, be aware that it takes a few weeks to a few months for the Petrifix to clarify. It takes a while for 100% of it to stick to the soil. And while it's doing that, you might have some black water. Typically not advised to send in a sample if you have darkened water that's above 100 milligrams per liter. This has been independently verified by a third-party lab to say that you are safe below that. You can get good results below that. I would encourage you to look at our online resources, and we do have a document available for you that gives the state of the practice, state of the art for groundwater sampling with colloidal carbon that I put together with our team that goes over this concept plus other best practices for getting a good groundwater sample after the fact. So I always like to mention that, so in case you plan a sampling event too soon after that you're prepared. So we can also provide currently some free field concentration kits that you can quickly in the field use a colorimetric analysis. Very easy to do. It just takes bottled water to measure the concentrations in the field on your own when you desire to do that, so you know if you can send the sample to the lab. So with that, I realize I'm rushing a little bit just because I want to have more time for Q&A. So Amanda, why don't we turn it over to you on this?
That's great. Hang on, let me just put my camera back on. Yeah, thank you, Todd. That was really, really a great presentation, really clear, and some really useful tips there for the field. I can see some questions have come in. I just wanted to say to everyone before we start going through them, if you think of any other questions or you haven't posted anything yet, and you can think of some more, do feel free to keep posting them, and I'll do them best to pick them up as we go along and fit them in. Right then, let's have a look. Let's start with the first one. There's here a question about LNAPL. Can it be used with mobile LNAPL of a 5 centimeter thickness? I don't know, Todd, if you want to take this one.
Sure, no, thank you. That's a very important question. Thank you for the person who answered that or asked that question. 5 centimeters thickness. The way I look at this is the rule of thumb is that Petrifix, first of all, is not designed to treat LNAPL. It doesn't have the amount of carbon or electron acceptors to come anywhere close to handling that level of stoichiometry. In terms of controlling the groundwater flux, our rule of thumb is to apply Petrifix after you have recovered or removed mobile NAPL on your site through other means. It could be mechanical removal or even through in situ chemical oxidation. So that's generally what you want to think about. Get rid of the worst soil mass, get rid of the worst LNAPL. The Petrifix will do a terrific job at that point moving forward.
That's great, thank you. Right, next one. Can it be used on PAHs and on chlorinated solvents? I don't know which of you wants to take that one.
I can take this one.
Right.
So on PAH, yes. So basically, the technologies has been studied for the petroleum hydrocarbons on, I would say, the wide family. So it's TPH, it's BTEX. In some cases, we can treat also oxygenates, so MTBE, ETBE. This typically goes with the addition of ORC advanced, so to enhance their aerobic biodegradation, because this is an easier pathway compared to the anaerobic biodegradation. And also they can be used for PAH, so the polyaromatic hydrocarbons chain. It's not designed for chlorinated solvents, though. This is because the product, the formulation, comes together with electron acceptors. These are nitrates and sulfates. These are beneficial to hydrocarbon products, contaminants, but cannot be used for chlorinated solvents remediation. So the effect would be that these nitrates and sulfates would unfortunately inhibit the biodegradation process of the chlorinated solvent. So it's specifically designed for petroleum hydrocarbons.
Okay, great. Thank you, Marcello. The next one then, it's about the analyzing TOCs that you talked about earlier, Todd, I think. Do you advise to verify distribution analyzing TOCs on all sites? I think you're muted. I'll unmute you, Todd.
All right, there, thank you. So I do recommend verifying distribution on all sites, primarily through observations of darkened water. That's the cheapest and easiest to do. That would be adjacent monitoring wells within the radius of influence. It would be temporarily installed, I'll call them monitoring piezometers. I'm not sure if it's called the same everywhere in Europe. And I would say secondarily, soil samples looking for coloration. The TOC samples are not needed. That was more for more of an expensive research project where he needed to know more of the actual analytical concentrations for comparison purposes. But for documenting distribution in the field, visual observation is really sufficient for this technology.
Okay, great, thank you. Yeah, I've seen this question come in before. It's quite a good one, really. What's the difference between PlumeStop and Petrofix?
I'll take that one. Yeah, I actually meant to put that slide in, but the presentation was getting long. The very common question, very good question. So for those of you who are familiar with PlumeStop, okay, that's our flagship technology that came out before Petrofix. And the difference is this, is that technology is ideally suited for, say, PFAS. It's ideally suited for chlorinated solvents. And there's a couple of reasons why. So PlumeStop has the use of more of our patented chemistry, uses more of our polymers and dispersant chemistry for it to travel much farther in situ than Petrofix can. Petrofix doesn't have the same chemistry and it can't travel farther. So the column experiment that I showed earlier where it just stopped and didn't move, Petrofix is going to tend to just stop much sooner. We have to use tighter spacing. The other difference that's important, though, is that the hydrocarbon sites tend to be higher in concentration, and so Petrofix does have more activated carbon in it to better handle petrol filling stations. So that's a bonus. Third, Marcello mentioned this, is that it has blended electron acceptors that are in it as both part of the manufacturing process and added after the fact that are specifically designed, say the nitrate and sulfate, for hydrocarbon treatment. In fact, they would be detrimental to the use on a solvent site. So you can't really use Petrofix for a solvent site.
That's great, thank you, Todd. Just looking at the time here. Yeah, I think we have time for a few more. Let's just keep going. Right. This is not very specific, but when do I need to re-inject? I don't know who wants to take that one.
I can take this. I would say the key part of Petrofix, but also PlumeStop that was mentioned before, is about the fact that it is one single campaign technology. So it is specifically being designed for allowing the contaminants first to be sorbed to the activity carbon, but once they are sorbed, they are still accessible for destruction technology, so they are accessible to biodegradation. This means that the activated carbon would not arrive to breakthrough, would not arrive to saturation, because there is the biodegradation which supports the regeneration. So I wouldn't need to re-inject over time. And this is, I believe, one key part that makes this technology very interesting, very attractive, because, for example, if we compare to ISCO technologies, they are, by default, they need to be re-injected over time. But also, if we are thinking to aerobic biodegradation, if we are, for example, injecting ORC advance on a barrier, then after 1 year, we would need to re-inject to have an extra oxygen release. This is not needed with Petrofix. So unless we have not done I would say, a proper job. So maybe like the conceptual model was not detailed enough, or the injection did not go properly. So we need to go back to site to readjust the application. Otherwise, this is typically designed for being as one single application technology. And this is also why it is mostly typically applied via direct push, because in this way, the application becomes easier and becomes more cost effective.
That's great. Todd, you agree with that? You want to add something, or you're okay with that answer?
No, thank you. Yeah, I think I'm fine with that. Thank you.
Great. Right, the next one. Will Petrofix damage tanks if you flood around them? Yeah, this is based on the example you showed earlier.
Yeah, another good question. I would wonder the same thing. So colloidal carbon in the electron acceptors they're non-corrosive, and they're non-toxic, but more importantly, they're non-corrosive for that. So no, there's going to be no effect to the tank basin. There are a certain number of tanks that we will run into occasionally that are old, that might be metal, that have, in the United States, they're called induced current systems, where they're fed electricity to prevent corrosion. Now, the addition of additional sodium can change the current on that. So it doesn't corrode anything, but you would just have to be aware of that and make a calibration on that unit. But other than that, there's no effect. So you're safe.
Great. Right, so I think we have time for 2 more quick questions. Let's choose this one. Can I co-apply Petrofix and use it with ISCO?
Shall I take this?
Sure.
Okay. Yes. So I would say we can think about a treatment strategy, which foresees on the same side ISCO and Petrofix, and we have done this sometimes. Typically, this is not very frequent. Sometimes we hit the source with ISCO, and then there is a Petrofix barrier on the plume. This can be done. But thinking about on the same portion of the site about an ISCO phase before and a Petrofix later could be done, but in majority of the cases, this is not necessary. Basically, Petrofix almost covers the same concentration range for applicability as ISCO does. So this is why this is not very frequent. But technically speaking, this can be done. Typically, you would not co-apply them together and co-inject. This would be more a concept of separate phases.
Okay, more like a treatment train. Great. Okay, right. Last question then. Can it be used for soils?
Yeah, I'll go ahead and answer that, Marcello, unless you want to add to that. So I like to say Petrofix, the name is not specific to groundwater or anything. So it makes sense. It's a natural question to get asked. The Petrofix is designed as a groundwater treatment technology, and it does some limited soil treatment. So look at it this way, is that we are injecting it to treat groundwater plumes, and when we do that, we put enough activated carbon and electron acceptors to not only treat everything in the estimated pore space, but amounts that are going to diffuse off of soils back into the aquifer. And so those contaminants that come back off into the aquifer as we're treating, we're going to treat, and therefore you're going to get some soil cleanup. However, what we're attempting to do, it's not at the levels at the stoichiometry needed for thousands of milligrams per kilogram that people who are interested in soil remediation often need. And so by and large, it's not designed for the type of soil treatment that people are thinking about, and therefore should really be viewed as is the groundwater treatment solution that they may be looking for.
Great.
But Shell, I don't know, yeah, I don't know if you want to add into that.
No, I think it was more than very clear.
Clear enough. Yeah, great. All right, I think there's a couple more questions, I think, that I either may have missed, and there's a new one coming in as well, but we've run over time already, so we'll leave it at this. But if, yeah, so for the people who just whose question hasn't been answered, we will get back to you individually via email within the next few days. Also, if you think of a question later, you can email us at europe@regenesis.com. Before we close then, I just want to highlight, in case you're interested in learning more about Petrofix, accessing some of the documents that Todd has mentioned in the presentation, or look at any of our other technologies such as plume stop or other treatment solutions. We have a wealth of resources available on our website, so I do encourage you to explore those. Now, just to reconfirm, in the next hour or so, you'll receive an email with your attendance certificate already attached. And inside this email, there's also a link to a short feedback survey. Now, it would be great if you can fill this in. It's always super useful for us to get some feedback, especially for our speakers, and it will also help us plan our future webinar topics. So yeah, with that, I'd like to thank you again for joining us and have a great afternoon. Bye-bye.
Thank you.
Bye-bye.
Thank you, Amanda.